Hello everyone. Today we will be beginning our discussion of networks and trees. Now to start off with, we're going to go ahead and define networks and trees. So a network we can think of as being basically any connected graph, meaning graphs that are all in one continuous piece. So I have an example of a network drawn over here on the left side of the board. Notice this is all in one piece, even though this is not a complete graph, meaning not every vertex is connected to every other vertex, but it is a connected graph. Therefore, this is a network. Now, networks can represent a whole variety of things. We can have either networks that are organic, meaning that they are not planned ahead of time, they just sort of form by themselves. An example of this would be something like friends on social media, for instance, showing connections between people. They could also be planned. An example of this might be something like a power grid, where we have a very structured network that is planned out ahead of time before it is created. Now, when we have networks, one concept that sort of comes into play here is what we call degrees of separation. And the degree of separation between two vertices in a network is basically just how many edges do we have to travel, or what's the lowest number of edges that we have to travel to get from one of those vertices to the other one. So let's look at a couple examples of this. So looking at our graph over here on the left, first we want to find the degrees of separation between A and B. Well, this one's really easy for us because A and B are directly connected to each other, so we only have one edge between A and B. Therefore, the degrees of separation the degree of separation between A and B is going to be 1. Next we have D and G. Now this one's a little bit more complicated because we don't have any edges connecting D directly to G. So the shortest path that we can take to get from D to G would be going to E, then F, then G. So that's 3 edges, therefore we have 3 as our degree of separation. Now, notice that if we wanted to, we could have gone D, B, E, F, G, and taken 4 edges. Why do we not do that? Well, because when we're trying to find the degree of separation, we want to use the minimum number of edges possible to get from one of those vertices to the other. So if we go D, B, E, F, G, that's taking 4 edges, which is not the shortest path that we can take to get from D to G. The last one that we'll look at is from A to L. So the shortest path that we can take to get from A to L is going to be B, E, F, I, K, L. So we are taking 1, 2, 3, 4, 5, 6 edges. Therefore, we have 6 degrees of separation between A and L. One other notable thing about these two vertices A and L is that they are the 2 vertices that are the farthest apart in the entire graph. Now, what we call the degrees of separation between the 2 vertices that are the farthest apart is the diameter of the network. So we abbreviate this D. So in this case, we would say that D equals 6. So this is our diameter of the network. When we say that, for instance, the diameter of a network is 6, that means that there have to be 2 vertices that have 6 degrees of separation between them, and there cannot be any 2 vertices that have more than 6 degrees of separation between them. So this is the maximum degrees of separation that we have between any 2 vertices on the graph. Now, related to networks is the concept of trees. Now, I have a tree drawn for us over here in the bottom right. All a tree is, basically it's just a network that does not have any circuits. So if we look at this graph, for instance, we notice that there are no closed circuits anywhere in here. And there's a couple key properties that sort of go along with this. One of them is that because there are no circuits between any 2 vertices, there's only one possible way that we can get from one to the other. So going from A to D, for instance, we have to go to C, then E, then D. There is no other way to get between those 2 vertices. Another property related to this is that when we have a tree, every single edge is a bridge, meaning that if we were to get rid of any of these edges in this graph, it would no longer be a connected graph. In other words, it would no longer be all in one continuous piece. Finally, when we have n vertices, so in this case n is our number of vertices, so that's 6 for this tree. Anytime we have n vertices, we are always going to have n minus 1 edges. So in this case, we have 1, 2, 3, 4, 5 edges. So this is going to be the number of edges that we have anytime we have a tree. This brings us to the concept of the redundancy of a network. Now, the redundancy of a network is basically just however many edges that network has beyond what is needed to form a tree. So a tree always has the minimum number of edges needed to connect all the vertices that are in it. So any graph that has more than that has a redundancy of 1 or more. So for any tree, the redundancy is going to be 0. How do we know that? Well, when we are figuring out the redundancy, we basically are going to take the number of edges that we actually have and subtract n minus 1, which is the number of edges that we need to form a tree. So any tree is inherently going to have a redundancy of 0. Now, if we wanted to figure out the redundancy for this other network that we were looking at before, what we would basically do is we would first figure out how many vertices do we have. That would be n. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 vertices. So n minus 1 is going to be 11. And then we need to figure out how many edges do we have. So in this case, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 edges. So we use m for the number of edges. Now if we want to find the redundancy of this network, we're just going to use this formula right here, m minus n minus 1. That's going to give us 16 minus 11, meaning that we have a redundancy of 5 for this network. So what this basically means is that we have 5 more edges in this network than what we would need to be able to form a tree. Thank you for watching, and as always, if you have questions, I am happy to answer them.